This PowerPoint presentation is from section 14.7 of our OpenStax textbook and covers titrations. This is part 2 of the videos from this section. In this presentation, we will look at titration calculations for a weak acid, strong base titration. This is the problem from our Chapter 14 handouts. Calculate the pH value for the following weak acid, strong base titration and plot the resulting titration curve on the graph. We're going to be titrating 50 milliliters of 0.1 molar acetic acid with 0.1 molar sodium hydroxide and calculating the pH at the following different amounts of base added. Remember some of the problem-solving strategies that we covered in the last video. You want to first identify what your major species are and look for any reactions that will go to completion. These, remember, are the ones that involve a strong acid or a strong base. We'll do the stoichiometry of these reactions in moles first. If after that we're left with solutions containing weak acids or bases, we'll deal with those equilibria using ice tables or the Henderson-Hasselbalch equation. We also need to remember that the volume is constantly changing in a titration, so we'll need to do the reactions in moles and then divide by the new total volume at the end. So let's look at the first question. We're asked to calculate the pH of the solution before we've added any of the hydroxide base. Remember that pH is defined as the negative log of the concentration of H+. So in each of these questions, since we're trying to find the pH, we're really asked to find the concentration of H+. What are the major species in our system? At the beginning, we only have our acetic acid solution. And of course, that's in water. We haven't added any base yet, so what we have now is just a solution of a weak acid. We know how to deal with these. A weak acid will dissociate in water. To form the H+ ion and its conjugate base, in this case the acetate ion. Since this is a weak acid, we're going to be dealing with this as an equilibrium, so we need to know the Ka for this reaction. If we look that up in our reference table, we find that it's 1.8 times 10 to the minus 5. And again, since this is a weak acid, we're going to make an ice table to solve this. Since we're not changing the volumes here, because we haven't added anything yet, we can go ahead and deal with this one in concentrations like normal. Our acetic acid concentration starts off at 0.1 molar, and we'll assume 0 initial concentrations of the H+ and the acetate ion. For our change row, we'll have minus X and plus X, giving us equilibrium concentrations for the acetic acid of 0.1 minus X and X for the H+ and the acetate. Our Ka expression will be the product concentrations over the reactant concentrations. And we can put in the values from our ice table. We have X squared over 0.1 minus X. Since our K value is small, it's probably an okay assumption to assume that the X is small relative to 0.1. So we're going to have 1.8 times 10 to the minus 5 is equal to X squared, or approximately equal to X squared over 0.1. Solving that for X, we get X is equal to the square root of 1.8 times 10 to the minus 5 times the 0.1. And we find that that gives us a value of 1.34 times 10 to the minus 3. This is our value of X, And since X was our H plus concentration, this should also be the concentration of H plus. We should check, is this X value actually small relative to 0.1? And when we do the check on that, yes, it's about 1%, so we're okay in our assumption. So now we can plug that into our pH equation. To find that the pH of the solution before we add any base is 2.872. Let's look at the next problem. Here we're asked to calculate the pH after adding 4 milliliters of base. Just as a reminder, we're always looking for the concentration of H plus if we want to calculate the pH. So what are our major species this time? Well, we're titrating our acetic acid, and now we're starting to add the sodium hydroxide. Because we're adding a strong base, we see that we're going to have a reaction that will go to completion. The acetic acid will react with the sodium hydroxide. Since we have a strong base, we'll use a single arrow to represent that this reaction goes to completion. We'll form water and sodium acetate. We want to deal with this reaction using moles, and we'll set it up as a stoichiometry table. To fill in our initial row, we need to find out how many moles of acetic acid we started with. We had a 0.1 molar solution of acetic acid. And we had 50 milliliters of this solution to begin with. So doing the math on that, we find that we're starting with 0.005 moles of the acetic acid. How many moles of sodium hydroxide are we adding? Well, its concentration was also 0.1 molar. But we're only adding 4 milliliters of this solution. So we're going to be adding 0.0004 moles of the sodium hydroxide. Again, we'll start with 0 of our products. For the stoichiometry change, again, we'll have minus X for each of the reactants, plus X for the products. We'll notice that the sodium hydroxide is our limiting reactant. So we expect at the end that this species will go down to 0, which means that our X value is going to have to be the 0.0004. When we subtract that number from the 0.005 moles of acetic acid that we started with, we get 0.0046 moles of the acetic acid that are left, and we'll be producing 0.0004 moles of the acetate ion. Now, what do we have in our solution? What are our major species at this point? We've gotten rid of all the sodium hydroxide by neutralizing some of the acetic acid. So what we have now are acetic acid, and we have the acetate ion that we've produced. This is a solution of a weak acid and its conjugate base. We should recognize that solution as a buffer. How did we solve for the pH of a buffer solution? We used the Henderson-Hasselbalch equation. The pKa of acetic acid is 4.74. The concentration of A- will be the moles of A- that we produced divided by the new total volume. What's our new total volume? Well, we started with 50 milliliters of the acetic acid solution, and we've now added 4 milliliters of base. So our total volume is going to be 54 milliliters, or in terms of liters, 0.054 liters of solution. In terms of the acetic acid, whoops, I lost a zero here. We have 0.0046 moles of the acetic acid over that same total volume. Sorry for running out of space here, but we have everything filled in that we need to, and I'll just write the pH up top. When we calculate that, we get a pH value of 3.68. So adding the base has increased the pH of the solution. In our first, before we added any base, we had a pH of 2.872, and now after adding 4 milliliters, we have a pH of 3.68. Part C asks us to find the pH of the solution after we've added 25 milliliters of base. Something to point out here, we're titrating 0.1 molar acetic acid with 0.1 molar sodium hydroxide. Since this is a one-to-one reaction and we're having equal concentrations of the reacting species, since we're starting with 50 milliliters of the acetic acid, we expect the equivalence point to occur when we've added 50 milliliters of base. So when we're adding 25 milliliters of base, we're about halfway, well, we're exactly halfway to the equivalence point actually. Okay, so let's go back and follow our series of steps. What are the major species that we have? Like in the last one, we have our acetic acid that we're titrating, and we have the sodium hydroxide that we're adding. These will undergo a reaction. Form water and sodium acetate. Again, we'll do the stoichiometry table. We had already calculated that our initial amount of acetic acid was 0.005 moles. In this case, we're adding 25 milliliters of sodium hydroxide. It's 0.1 molar. So we're adding 0.0025 moles of the hydroxide. Again, we'll assume initial 0 amounts of the, obviously water is not relevant, but 0 of the sodium acetate. We'll do our minus X for reactants, plus X for products. Our sodium hydroxide is still limiting. It's the one there in the smaller amount. So that will go down to 0. Our X value therefore must be 0.0025. When we subtract that from the initial moles of acetic acid, we get 0.0025 moles left, and we'll produce 0.0025 moles of the sodium acetate. After the stoichiometry reaction, what are our major species? We still have acetic acid left, and we have some acetate ion that we've formed. All of the hydroxide has been used up. Again, we have a solution of a weak acid conjugate base pair. This is a buffer. And the Henderson-Hasselbalch equation is a great way to calculate the pH of a buffer. pH is equal to the pKa plus the log concentration A minus over HA. Our pKa was 4.74. We need to put in the concentrations of the A minus and the HA. So the A minus, we have 0.00250 moles of that. Our new volume is 75 milliliters or 0.075 liters. And in terms of the acetic acid, we also have 0.0025 moles. And the volume is also 0.075 liters. Notice that at the halfway to the equivalence point, we have used up half of the acetic acid by converting it to the acetate ion. So the concentrations of the weak acid and its conjugate base at this point in the titration are equal. The log of 1 is 0, so that gives us that the pH is equal to the pKa, in this case 4.74. This is an important point in the titration. It's called the half equivalence point, and it's a valuable point in the titration because the pH at this point is equal to the pKa. As we'll see later, we can use this to find the pKa of an unknown acid that we're titrating. So let's continue. Part D asks to find the pH when we've added 49.9 milliliters of the base. Remember that we've already decided that our equivalence point should be at 50 milliliters of added base. So at 49.90, we're just shy of the equivalence point. We still have major species of the acetic acid that we're starting with, and the sodium hydroxide that we're adding. These two components will react with each other. in a reaction that'll go to completion to form water and sodium acetate. We'll set up our stoichiometry table. Our initial moles of acetic acid we calculated before to be 0.0050. This time we're adding 49.9 milliliters of the 0.1 molar sodium hydroxide. That's going to give us 0.00499 moles of sodium hydroxide that we're adding. We assume 0 initial products. Stoichiometry change minus x plus x. We still have less sodium hydroxide than acetic acid, so the sodium hydroxide is our limiting. That's going to go down to 0. And when we subtract 0.00499 from our initial moles of acetic acid, we get 1 times 10 to the minus 5 moles of acid left over, but we've produced 0.00499 moles of acetate. We still have a buffer made of a weak acid conjugate base pair, so we'll use again the Henderson-Hasselbalch equation. pKa of acetic acid is 4.74. The A minus concentration is 0.004990 moles. The new total volume is going to be 99.9 milliliters or 0.0999 liters. And our acetic acid concentration is the moles over the total volume. And plugging that all in gives us a pH value of 7.44. Part E is at 50 milliliters of base added, and yay, we've reached our equivalence point. So this is the point where we've added the exact amount of sodium hydroxide to react with the acetic acid that we already had. So if we just go ahead and write that reaction, and set up our stoichiometry table, since we have equal amounts of acetic acid and sodium hydroxide, neither one is limiting, and in fact, both of those concentrations will go to 0, but we'll be producing 0.005 moles of the sodium acetate. So what is our major species now? We've actually gotten rid of the acetic acid and the sodium hydroxide in the reaction, and now we have a solution of sodium acetate. We know that sodium acetate is a weak base. Well, actually, sodium acetate is a salt, but the acetate ion is a weak base. So what we have now is a solution of a weak base. How does that affect the pH of the solution? Well, we know that the weak base is going to react with water, form hydroxide ions, and a little bit of acetic acid. This is a reaction that produces hydroxide ions. We have a weak base. So what we need here is to set up an ice table. And we're going to solve this in terms of the Kb value of sodium acetate. So we need to find the Kb of sodium acetate. That's going to be equal to the Kw over the Ka of acetic acid, which is 10 to the minus 14 over 1.8 times 10 to the minus 5, which gives us a value of 5.56 times 10 to the minus 10. So what is our initial concentration of acetate ion? Well, we made 0.005 moles of acetate, and our new total volume is 100 milliliters. We had the 50 milliliters that we started with and adding 50 milliliters of base. We'll assume that we start with 0 hydroxide and 0 acetic acid. In our ice table, we have minus x plus x plus x. So here we have 0.05 molar minus x of the acetate, x and x of our two products. So setting up our K expression, product concentrations over reactant concentrations, we have x squared over 0.05 minus x. And again, since our K value is pretty small, it's probably an okay assumption to neglect the x in the sums and differences. So when we solve this for x, it's going to be equal to the square root of 5.56 times 10 to the minus 10 times the 0.05, which gives us an x value of 5.27 times 10 to the minus 6. What does this value represent? Remember that x was our concentration of the hydroxide ion. I'm going to create myself a little space over here. We want to calculate the pH, which is minus log of the concentration of H+. So we have to convert hydroxide concentration into H+ concentration in order to solve this. If the hydroxide concentration is 5.27 times 10 to the minus 6, H+ concentration will be 10 to the minus 14 divided by that. So the H+ concentration is 1.8975 times 10 to the minus 5. Sorry, it's getting a little crowded up here. But anyway, when we plug that into our pH equation, whoops, I had the, sorry, it's not 10 to the minus 5, it's 10 to the minus 9. And the negative log of that gives us a pH value of 8.722. So the pH at the equivalence point of this titration of 0.1 molar acetic acid with 0.1 molar sodium hydroxide is 8.722. This might seem a little surprising that it's greater than 7. When we titrated the strong acid with a strong base, remember at the equivalence point, we had a solution that had a pH of 7. This is typical. Having a pH greater than 7 is typical when you titrate a weak acid with a strong base. Why? Because what do you have after the stoichiometry reaction? You've created a solution of a weak base. Weak bases will have pHs greater than 7. Okay, thanks for hanging in there with me, guys. I promise we're getting there. All right, so question F says, what will be the pH after adding 50.10 milliliters of the sodium hydroxide? If it took 50 milliliters to reach the equivalence point, we are now sort of after the equivalence point. So hopefully you can see that we've gotten rid of all of our acetic acid by reacting it with the sodium hydroxide. And in fact, we have extra sodium hydroxide. So what are our major species? All of the acetic acid is gone. It's been converted to acetate. And we have a little bit of hydroxide left. Both of these species are bases, so they won't react with each other. But which is going to be the major contributor to our pH? Is it going to be the weak base or the strong base? As you can probably figure out, the hydroxide is going to be the major contributor to the pH of the solution. So we need to figure out how much extra hydroxide we have. Since it took 50 milliliters to reach the equivalence point, the extra is coming from the 0.1 milliliters extra that we've added. How many moles is that? The first 50 milliliters neutralize the acetic acid. The remaining 0.1 milliliters creates this extra 1 times 10 to the minus 5 moles of hydroxide. What's the concentration of hydroxide in this solution? It's the moles divided by the new volume. So we had 50 milliliters plus 50.1 milliliters gives us a little over 100 milliliters, or 0.1001 liters. This gives a concentration of 9.99 times 10 to the minus 5 molar. And we convert that to the H plus concentration and then take the negative log of that to get the pH. We find that we get a pH of 10. At 70 milliliters of base added, we also have extra hydroxide, 20 milliliters worth of it. or 2 times 10 to the minus 3 extra moles, in 120 milliliters total solution, or 0.12 liters, gives us a hydroxide concentration of 0.0167 molar and a pH of 12.22. So let's go ahead and now plot these values that we've calculated onto our pH titration curve. Notice that we get sort of an S-shaped curve as we predicted. Let's highlight several important points in the titration. When you start the titration before you've added any base, you only have a solution of weak acid. And remember that we use equilibrium ideas and ice tables to calculate the pH of a weak acid solution. Once you start adding base, you convert some of the weak acid to its conjugate base. This is what we call a buffer region. You have significant concentrations of both the weak acid and its conjugate base. So in this region of the titration curve, we did all our calculations with the Henderson-Hasselbalch equation. We also identified a very special point in this buffer region. It's called the half equivalence point, and it's when the pH of the solution or the titration is going to be equal to the pKa of the acid that you're titrating. Another special point is the equivalence point. This is when you've added exactly the right amount of base to neutralize the acid that you have. At this point, you have a solution of A minus, or a solution of the weak base. And therefore, for the titration of a weak acid with a strong base, the pH at the equivalence point will be greater than 7. After the equivalence point, we have a situation where the pH is dominated by how much extra hydroxide that we've added. And so the calculations here are based on the concentration of the extra hydroxide. So we've identified sort of 4 different regions where the calculations are different for a pH titration curve. I'd like you to take a moment to complete the following table regarding the titration of a weak acid with a strong base. Label the diagram with where the NaOH titrant is, where the weak acid solution is, where are we going to put the indicator, and then in the table, identify the major species and the pH at the various points in the titration. Pause the video as you complete this task. Okay, so remember that the titrant is what's added with the burette. So we use the sodium hydroxide in the burette. And in the Erlenmeyer flask, we have our weak acid and our indicator. Before we've added any base, the major species in our solution is just the weak acid. Weak acids will have pHs less than 7. And we also will have a pH that's less than the pKa of the acid. At the halfway equivalence point, we will have both HA and A minus. In fact, they'll be there in equal amounts. And the pH will be equal to the pKa. Where it falls relative to 7 depends on the pKa of the particular acid. At the equivalence point, we have converted all of our weak acid to the conjugate base. The pH will be greater than 7 and greater than the pKa. Well, after the equivalence point, our major species are A minus and hydroxide, where the pH is going to be controlled by the concentration of the hydroxide. And again, our pH will be greater than 7 and also greater than the pKa. In this video presentation, we walked through the calculations of a weak acid strong base titration. We identified some important points in the titration curve and emphasized the important problem-solving strategies. You should now be ready to try group problem number 17 that covers a similar problem, except it is the titration of a weak base with a strong acid. All of the same problem-solving strategies will still apply.